Good morning, chemists. Welcome to lecture 18 of chemistry 132b, quantum principles. I realize that a week from now we have the second midterm, and that indicates that time is moving pretty quickly this quarter once again. Can't believe next week is going to be week number 8. But that's how it is. And at the end of week number 8 on Friday, there will be another quiz or test, whatever you would like to call it. And it will be run in pretty much the same fashion. Of course, we will have this time the monitor option in Canvas active so that we can see what you guys are doing in addition to the lockdown browser. So that will be the idea. The test is going to be run through Canvas. As before, it's going to be about the same length. And we will be posting a practice test, which is, very representative of the questions that you will be getting. Of course, the questions that you will be getting are, questions you haven't seen. So it feels like it's more difficult than the practice test. But I assure you that the practice tests are composed of questions from previous exams, and people before you had exactly the same complaints about those exams. It's just difficult to do a test with questions, of course, that you don't know the answers to. So, but that's why I really strongly suggest that if you do the practice test, don't look at the answer too quick. Just try to do the test and pretend it's a real test, and then see how well you are able to solve those problems, right? So just literally test yourself and see how well you can do an exam of this kind. We will say more about the upcoming midterm as we go along. I will say some things on Monday and Wednesday next week so that everybody is clear on what to expect and how to prepare. I can tell you that the material that will be on the second midterm is not cumulative, so it's not everything we have talked about thus far. Instead, it's about the material covered in lectures 11 to 18, and 18 is today's lecture, so today's lecture is included, but not lecture 19 and 20 for next week. Okay, so those are not included in the material for the test. So, all right, so I will, it will be the same kind of exam. So you have open notes, right? So you can, any written material is allowed for you to use. You cannot use electronic gadgets and communicate with your buddies exchanging answers. That, of course, completely defeats the purpose and also doesn't tell you anything about what you know. Use the test as a mechanism to see how well you know the material. That's what it's for, right? Nothing else. It's really, that's the purpose of the test, just to see how well you can do this material. And it will be helpful for you to know what you can and what you cannot do, because that means that you can focus on certain aspects of the material that perhaps need a little bit more attention, right? So you can be proactive and ask the TAs or me to explain things one more time because, it didn't really sink in as much as maybe it should. So use the test rather than see it only as an opportunity to score the highest possible points for your transcript. Don't worry about that part yet. Like I said last time, focus on the material first. Your grade will naturally flow from your understanding, okay? Not the other way around. Okay, so the test is going to be quite similar to the test last time. So mostly multiple choice, some numerical questions as well, okay? Again, so we'll talk about the midterm a little bit more on Monday and Wednesday, so there will be no, I think, mysteries about the exam. We'll clarify everything that you want to know. For now, I will dive into lecture number 18, which is today's lecture, and we will start talking about a pretty exciting topic, I think, because thus far we have considered how atoms can be described in terms of quantum mechanics, in terms of wave functions, electron wave functions. We have a pretty good idea now what these things look like. definitely for the hydrogen atom, in which case we could solve the entire problem analytically, but even for other atoms that have more than one electron, like helium and every other element beyond helium, which has, of course, numerous electrons that have electron-electron interaction. The electron-electron interactions complicated the story a little bit, but we can still have very good approximate descriptions of the electron wave functions in atoms. And that's what we have been using. And the models that we have explain really well how the energy levels of the particular states are found in atoms. So we can explain almost everything that there is to know. Of course, the description gets more complicated if you add more electrons, but with the approximate descriptions, we can really get a pretty good handle on describing the atom. So today we are going to talk about the situation where the atom is not just by itself, okay? Because so far we only talked about the atoms as if it were just sitting by itself, not surrounded by anything else, right? And that's, of course, not what chemistry is all about. Chemistry is all about atoms interacting, forming bonds, chemical bonds. And that changes the situation quite a bit, okay? So today we're going to talk about that in terms of valence bond theory and a little bit in terms of molecular orbital theory, okay? So that's basically on the menu for today. Before I do that, I'd like to kind of remind you of some properties of quantum mechanical wave functions, okay? And that is basically the following. So let's assume we have an operator, a general operator, which I always indicate by omega. And this operator is operating on one of its eigenstates, one, in this case, number n of its set. It has a whole set of eigenstates, of course, as we know, but I just select number n from this set because number n has this eigenvalue, okay? So just omega. This is just a number. It's its eigenvalue. But now I'm going to have this thing operate on a second wave function, which I call m. And I'm going to say, well, n and m happen to have the same eigenvalue, okay? So that is just a particular situation. It doesn't have to be the case all the time. This is just a particular situation, which is a situation that these two wave functions are degenerate, right? That's the word that we have been using for this situation. If two wave functions have the same eigenvalue, think about this general operator here as the Hamiltonian, then in that case, this eigenvalue omega is, of course, the energy. That means these two wave functions will have the same energy, and therefore they are degenerate in terms of their energy. Okay, so why is this interesting? Well, let's say I'm going to do something now. I'm going to compose a new wave function. I call it psi. And I'm going to say, you know what? This is a linear combination of n and m. Okay, so I can write it as a sum, a linear combination of these two wave functions. Right, so we have seen this before. We can make linear combinations of wave functions that form a complete set. N and m are part of a complete set. So I can use them to describe any other wave function I want, in this case, psi. Right? This is a general principle that we've been talking about for quite a while now. What I'm asking myself is the following question. What happens if I operate on this new wave function? What are the properties of this wave function? So let's do that. It's not so hard to do because, I can just write down the wave function and operate on it with the operator. So it operates on the first part of the wave function, which is n. It will operate on the second part of the wave function, which is called m. Okay, and both of them are eigenstates of this operator, which means they will produce the eigenvalue omega. Both of them, and because they're degenerate, they produce the same eigenvalue. Okay, so they both produce omega. And what I can do then, I can take omega out of the equation and simply say that what I'm retrieving here is the following. Okay, so this is what I'm getting, and that, of course, equals omega times this wave function I just made. So this is a pretty unique situation. In the case of the two states being degenerate, aka they have the same eigenvalue. In that case, the linear combination of these degenerate wave functions, if I do that, then this combination is also an eigenfunction of the same operator. Okay, so if I think of this operator once again as the Hamiltonian of my hydrogenic system, okay, then what I'm doing here is I take two degenerate wave functions, I make a linear combination, and that is again a solution of the Schrödinger equation, and therefore a valid solution of my problem. Now this is, you may not realize this, but this is exactly what we have been doing with the p orbitals. Okay, I've been doing this with the p orbitals because in the p orbitals, let's say you have three p orbitals, right? They come in threes because they have projections ml equals -1, 0, and 1, right? So, but what we have been doing for the 1 projection, we call that pz. But the 1 and the -1 we have not been using. Instead, what we have been doing, we have been combining these two functions in a linear combination to construct px and py, right? And this is why this is allowed. It's allowed because if you make a linear combination of two degenerate wave functions, and these two guys are degenerate because they have the same energy, right? They have different ml values, but you know, they are having the same energy. So px and py are legitimate solutions of this Schrödinger equation, and therefore are equally valid than the projections ml equals -1 and 1. So the combination of these is also a valid solution of the Schrödinger equation. Okay, so that is good to know. Now, the thing is, if this omega here, in this case, omega is an eigenvalue for n as well as for m, right? But what if n and m have eigenvalues that are close but not exactly the same? Okay, so let's say that omega for the wave function n is approximately equal to the eigenvalue associated with wave function m. Approximately, but not exactly the same. What if I do the same kind of reasoning here? Well, of course, what you get then is something that is close, but not quite, okay? So if I make a linear combination of two of these functions that are not exactly having the same eigenvalue, then I'm not really getting this condition right here, okay? So that means that the new function here that I'm making is not necessarily an eigenstate, an eigenfunction of the operator that I'm considering, okay? Because they're not exactly degenerate, but it's pretty close. And this is the important part. The important part is that it's not too far off. It's a reasonable approximation. We know it's not exact. This line here is exact, but as soon as it's not exactly degenerate, it becomes approximate. But as long as these values are not too far off, we're still pretty close, right? So that is that's one important realization. We have been using it for pxpy, but now we're going to use it for a different situation, which is called valence bond theory. We're going to expand this concept, and keep in mind the general notion here is that I'm going to make a new wave function, okay, capital psi, which is going to be a sum, Cn, okay, of little psi, okay, where little psi are my hydrogenic solutions to the Schrödinger equation, okay? This guy is describing a new situation that is really hard to solve, but I'm going to express it in the complete set that is provided to me by the solution of the Schrödinger equation of the hydrogenic system, of the hydrogen atom. I'm going to use them as my way to build up a description of a more complex situation. This is approximate, but it is a pretty good one. Okay, so in what case are we going to do this? Well, it's a very important case, and that's the following. Okay, so far we have considered atoms being isolated. So let's focus on carbon, one single carbon atom. What are the orbitals here? We know what the orbitals are. The hydrogenic orbitals, in this case for carbon, are that it has, you know, the same kind of ordering, 1s and then a 2s and then a 2p. If you fill out the electrons according to the Aufbau principle, which is what we did last time, then we know that the 2s has a paired electron set, so electron pair. And then in the 2p, I have 2 unpaired electrons according to Hund's rule. Okay, so if I now try to draw this, I get the following. The s orbital that is fully occupied here, the 2s, and the 1s, both of them are fully occupied, are just spherical kind of orbitals that are surrounding this carbon nucleus. And then I have the 2p orbitals, of which there are 3, let's say one aligned along x, one aligned along y, and one aligned along z. Okay, but there's only 2 unpaired electrons, one in one of them and the other one in another one. Okay, so that means, let's say it sits, one of them could be in the y-oriented p orbital, and the second one could be along px. This is arbitrary. It could be in any one of them, of course, right? So this is then what I'm getting. And so if I now ask myself, if I'm going to make a methane molecule out of this carbon atom, how is that going to work? Okay, because some way, somehow, the electron density is indicated by these orbitals. That is what the electrons are. Okay, so tentatively, that is where a bond is going to be formed, because bonds are being formed by electrons. Right, so I need to put hydrogen atoms closer to this carbon atom, and then there needs to be a bonding formed between the electrons provided by the hydrogen and the electrons provided by the carbon. So if I look at this picture, what I would do intuitively is this. I'm going to add 2 hydrogen atoms to it. Okay, each hydrogen has 1 electron available to form a covalent bond. Right, so this atom here with 1 electron can hook up with the lone electron here in one of the 2p orbitals. The second one can hook up with the second unpaired electron in the p orbital. Then I'm kind of running out of options, because I already know that those 2s electrons are already paired, and it's very unlikely that these unpaired electrons will now be ready to bond with another hydrogen atom. Okay, so that is one complication. So how is this going to work? How is this 2s orbital going to contribute to the bonding? In this model, it's not clear at all how that is working out. Right? And the other problem that I'm having is I can only put 2 hydrogens here, clearly, and they are aligned in a very funny way, because they are aligned along the axes that I'm thinking that the p orbitals are aligned at. Right? So this is a 90-degree situation here. There's the first H and the second H are forming a 90-degree angle. I know this doesn't look anything like methane. What I know about methane is that these angles are definitely not 90 degrees. This is very unfavorable, pretty close. It's going to be repulsion between the 2 hydrogen atoms. And so this is a very unfavorable situation. How can I reconcile this, knowing that the orbitals are like this? This makes no sense. Did we do something wrong? Or is there another explanation? So there is another explanation, of course. And the main idea behind this is, it's actually very important to see this distinction. Okay, the main distinction between what we have been talking about now so far and what we're going to talk about next is that a single atom of carbon indeed has the orbitals aligned and oriented like this. So this is the electron density of an isolated carbon atom. This is the lowest possible energy that the carbon atom can be in, and in that case, if it's all by itself, this is the orientation of the orbitals. This is the electron density around the atom. But if you put the atom in a different surrounding, if you put other charges next to it, which means other atoms, because other atoms have nuclear charges, they have electron charges, there's going to be a whole set of new interactions between the electrons of the carbon atom and the surrounding charges that you are going to put now pretty darn close to the carbon. This means that the situation is completely different. This is not an isolated atom. This is no longer the Schrödinger equation that we solve for the carbon or the hydrogen system. Okay, so it is different. It is not the same. And if it is different, that means we have to solve a complete new problem. Okay, so it's no surprise then that the solutions we found for the isolated atom are not fully representative of the situation when I'm going to put a lot of different things around it. It's a completely new situation. So what I have to do then officially is I have to solve this whole problem then for kind of hydrogen atoms surrounding the carbon atom, and then solve the Schrödinger equation of the entire system, including all the charges, take care of all those charges, all the interactions. And that is going to be a lot of work, and in some cases, impossible, okay? So we have to find an approximate solution to this, okay? We have to find an approximate solution to this. What we're going to find is something that looks like this, okay? So this is the tetrahedral arrangement of the hydrogen atoms around the carbon atom. And again, it doesn't look like the solutions of the hydrogenic orbitals, which form straight angles, and these angles are not straight because the angles between these orbitals that I'm seeing here are 109.3. Okay, so that is a significant difference. How can we explain, or how can we describe these orbitals? Where do they come from? Okay, so what we're going to do then is we're going to just try to describe the new system. The new system is a system with the hydrogen atoms around it in terms of the complete set that I had found previously. Okay, the complete set I found previously are the hydrogenic orbitals. These are the wave functions I'm going to use to construct the new situation. This is going to be approximate. This is not the real deal, because we are not solving the Schrödinger equation for the new situation. Instead, we're going to use the solutions from the old situation and make a linear combination to make a new wave function, build a new wave function that is better behaved and a better descriptor of the new situation. Okay, but that's what we're going to do. We're going to take the old wave functions, and these are the old wave functions. These are the good old hydrogenic wave functions that we have been talking about thus far. These are the wave functions of the isolated atom. Okay, they are well behaved. We know what they look like. We know what the energy levels look like. We also know what the orientations look like for the orbitals described by this set. This is a complete set. Okay, now I'm going to describe a new situation, which is described by this wave function here. It has an H. This H is going to stand for hybridization. Okay, but what it really is, it is a wave function that is going to describe my new situation, which is the situation of the atom being surrounded by a whole bunch of different charges, because you're going to put other atoms close to it. The theorem that we're going to use is the theorem we introduced very early in this course, and that is you can make a linear combination of the wave functions of a complete set, which is what I have right there. Okay, you just make a linear combination. That's what I'm doing here with coefficients, which are basically providing the weighing factors of how much of each kind of the wave function is going to be in the total description of the new situation. That is what this is. We have done this many times, but now we're actually going to apply this to this real kind of chemistry relevant situation, right? Now, I want to stress that what we're going to do is we're going to combine hydrogenic wave functions in a certain way to find a better description for the new situation of the atom being surrounded by other atoms. This is our guess, okay? So it's not exact. It is a best guess that is going to give us better solutions, better descriptions than if we take the individual hydrogenic orbitals, because those are not going to do the job for us. So we have to make adjustments by expanding the set with other hydrogenic orbitals, right, to find a new solution that is a better descriptor. This is the thought. This is the thought behind it. And of course, realize now that this new wave function I'm going to build is not an eigenfunction of the original Hamiltonian. Okay, it's not going to be an eigenfunction of the original Hamiltonian, because I'm going to use here eigenfunctions that have different energies. Okay, but these energies, as you will see, are going to be pretty close to the original ones. All right, and that means that there's going to be reasonable description. It's going to be a reasonably good approximation. Okay, so that is the thought behind this procedure. Okay, so what I'm going to do next is I'm going to construct orbitals in a variety of ways and then see if I retrieve symmetries and properties that are much better fits for what I know about the formation of chemical bonds. Right? So that is what I'm going to do here. So what I'm going to do is I'm going to now call this new wave function capital psi h. And we're just going to call it h. Okay. So this h stands for capital phi. I'm just going to drop the phi and just write it h because it's going to be just shorthand writing. The first kind of linear combination I'm going to make is I'm going to take a 2s orbital. I'm going to combine it with a 2pz orbital. And I'm going to call this the sp hybridized orbitals. Okay, this is what I'm going to do. I'm going to call it orbitals because there's two ways in which I can do it. I can either add the pz to the s or subtract the pz to the s. I'm going to call these new orbitals H1 sp and H2 sp. Now, if you ask yourself, what does this look like? It's this picture that you would probably have seen before. Here's the 2s, which is spherical symmetry. That is going to be the first one, this guy right here. I'm going to add pz to it. Pz is oriented along the z-axis. So if I make a linear combination with equal weights, okay, as you can see, so the c coefficients are 1, 1 for both s and p, you get the following result. You get the picture here. You get, this blue part is the in-phase part with the s, so it's going to constructively interfere, forming this big blob that points along the negative z-axis here. And then I get this guy here, which is partially destructively interfering with the blue part on this side, leading to kind of a small remnant of yellow, which is the opposite phase from the blue phase. And I get a little stump. So what I'm getting, an electron distribution, electron probability, which is very high for negative z, and a little stump here for positive z. This is the sp hybridized orbital. It's a new orbital, okay, that I'm using. I'm using the old orbitals to make a new one, and I'm hoping this new one is going to make a better description for my new situation, which is the situation of interest, the atom being surrounded by other atoms. Okay, here's the other one. This is the negative version. I just flip the orientation of the pz. Now, this phase here has a different sign, and that means, of course, that the result is the same, but now flipped 180 degrees. Okay, you get the little stump now at the negative values for z, for the z-axis, and this large blob, which is the constructive interference part, is now pointing along positive z. So I get two of these orbitals, okay, and they have different shapes from the original ones that I used to make them. So if I combine these two guys, these two new orbitals, I see that what I'm getting is this black dot here in the middle, this black dot here, that's it, is going to be the location of my nucleus. In this new kind of orbital, this new wave function I'm using, it has one extension to the left, one extension to the right. Those are the two sp orbitals. The little stumps here have very limited effect. Okay, so it's mostly, as also indicated here below, it is really one lobe that points along the z-axis and the other lobe points along the z-axis as well. So what do I get here? What is the advantage of doing this? The advantage is that I have now a new orbital description, an approximate one, but this is a really good description of the orbital in the case where there is alignment of electron charges along the z-axis. So the bonding is taking place along the z-axis. Okay, so that is really what I'm looking for. We're going to show some examples, but I'm first going to zip through a variety of combinations, of linear combinations that I can make of the original orbitals, and then we're going to use these new patterns to understand how atoms can have their orbitals oriented when they are surrounded by other atoms. So the sp2 hybridized orbitals, I think you all know what they are, but what you may not know is how you can construct them, and that is basically written over here. The first sp2 hybridized orbitals, H1 sp2, is the s orbital plus square root of 2 times the py. orbital. Okay. Again, this is an approximate description. This is no longer an eigenstate of the original Hamiltonian because the S and the Py, they could have slightly different energies, right? If you are going, for instance, to talk about carbon, the S2S for carbon and the 2Py for carbon are not having the exact same energy. So this is no longer a solution of the original Hamiltonian, but it is a much better description, pretty close to a solution of the new Hamiltonian. So that's why we're doing it. These hybridized functions are much closer to what the new wave functions look like using the new Hamiltonian. It's an approximation of the new solution to the new Hamiltonian. I cannot really solve the new Hamiltonian, it's too complicated, but this is the best approximation I can come up with that gets really close. This is the second one, okay? So now I have H2sp2. I combine again an S. Now I have also a portion of Px and a portion of Py. Okay, so this is one way, and you see now these coefficients are no longer 1, they have now different values. Third one, sp2h3. Again, all these h's are wave functions, okay? So please understand that. These are wave functions that are now linear combinations of the original wave functions. The third one has s minus a portion of px minus a portion of py, okay? These signs are very important because they are going to determine the orientation of my hybridized orbitals. Here they are. The first one is an s orbital plus px plus py. Okay, actually, this is not the first one. These are the second and the third one we're going to look at. And what they're going to do is they're going to form the following scenario. Okay, so here I have, let me circle them. So if this is y, okay, that's the first one. So this is h1. Okay, and then these two guys are h2 and h3. So you can see all of them are oriented in the xy plane, okay, because they're only composed of py and px orbitals. One of them is oriented directly along y, and the other two are like tilted a little bit away from y, so they also have an x component. That is, of course, these guys do that. Okay, so h1, h2, and h3 are right here. Okay, so these are new orbitals that I'm constructing. The nucleus sits right there. That's the little dot. Okay, so it looks like they're shifted here. So in reality, of course, the dots are all the same. So this is really what it looks like. You have a dot in the middle, that's the nucleus. And then you have these lobes emanating from it. And those are the sp2 hybridized orbital lobes. The little stump, the yellow stump, barely has any effect on the bonding. So we focus just on the extensions, the lobe here, the electron density that is indicated in blue. Okay, so we're going to continue sp3 hybridized orbitals. Everybody knows about sp3 hybridized orbitals, but maybe you don't know exactly how they are being formed. Here is the set of sp3 hybridized orbitals. H1 sp3 is, of course, a linear sum now of px, py, pz, and s. So I'm combining all of these guys, right, in a constructive sum. And here, the same, but now with different signs. Okay? And these signs are important, again, because these signs are going to determine the orientation of the hybridized orbital. So H2 looks very much the same, but there's negative signs in front of the px and in front of the py. This is number 3, H3 sp3. Now I have a negative sign here and a negative sign in front of the pz. And then finally, this is the last combination, the last linear combination of hydrogenic orbitals, and that is s plus px minus py minus pz. Okay, so what do they look like? These are familiar pictures. Okay, so what I'm doing is I'm taking the 2s, the 2px, and 2py, 2pz. I'm going to make a linear combinations. There's 4 possibilities, and these are the 4 possibilities. And they have these wonderful orientation, which is a tetrahedral form. Okay, so sorry, there was a question about the signs. I make linear combinations of S, P, X, P, Y, P, Z. But all of these, where I change the sign, are valid solutions, okay? All of them. There's 4 different ways in which I can combine these 4 orbitals. Okay, so I'm putting 4 orbitals in. I'm creating new orbitals, but I create 4. I don't generate more or less. I generate the same amount of orbitals. I cannot destruct or create new ones. Okay, I put old ones in, I get new ones out, but the number has to be conserved. And these are the only possibilities I can make that are valid. Okay, these are only permutations that I can make that are valid. Basically, the sign can either be a plus or a negative sign for the px. The s is always positive. So you get 4 possibilities of linear combinations that you can make. Okay, so this is the well-known tetrahedral orientation of sp3 hybridized orbitals. Okay, and that's of course a very, very well-known bonding pattern in organic chemistry. But it goes on, okay, it's not limited to the 2s and the 2p orbitals, because I can make combinations of the 3s with the 3p and the 3d. Why can I do this? Because the 3s, the 3p, and the 3d, for most atoms, are not too far away in terms of energy. They are not the same, okay? They are not the same. So the linear combination that I'm going to make from all these hydrogenic orbitals is definitely not an eigenfunction of the original Hamiltonian, but it is a pretty good description, pretty close to an actual solution of the new Hamiltonian. It's not the real actual solution, but it's pretty close to it. It's a pretty good approximation, okay? Because the S, P, and the D are not too far in energy, making this combination is not too outrageous, okay? If they are very disparate in energy, if they're really far away from one another, then this combination is probably not really a good combination to make, okay? That's going to be a pretty shoddy solution. The energies need to be close for the mixing of these orbitals to be efficient, to create a real a new situation that has new unique symmetries. This way, combining the 3s with all the 3 p orbitals and 1 orbital from the d set produces the following. It's sp3d hybridized orbitals. This is the trigonal bipyramidal symmetry that is well known in inorganic chemistry. Okay, I can go on because, of course, the d's have the same energies. They are degenerate. The d's are degenerate among themselves. So I can add, kind of at will, new d orbitals to it. Okay, in this case, I had added 2 d orbitals. So the first one is the 3dz squared, and the second one is the one over here. I combine these 2 with the s and the 3p orbitals. And if you do that, you have, of course, the sp3d2 hybridized orbitals, and they have this wonderful octahedral symmetry. Okay, so by making these linear combinations, I can indeed create symmetries that I know are happening in chemistry, and therefore these linear combinations are really good descriptors of my actual situation. Are they exact? No, but they are getting pretty darn close using the original set of hydrogenic wave functions with which I can work. Okay, this is why we're doing this, because this is a very workable solution. Okay, so you probably already know that these hybridized orbitals explain a lot of the bonding patterns in organic chemistry. Okay, so for the sp hybridized orbitals, if you take 2 carbon atoms, for instance, that are sp hybridized, then I have the electron density along the z-axis. Okay, so that's the sp connection that I'm making on axis. That's called the sigma bond. And then, of course, I have the 2 remaining p orbitals that do not partake in the hybridization. So I have 2 original p orbitals on each carbon atom that are not participating in the hybridization. They can form off-axis bonds, and therefore, for sp hybridized carbon atoms, I can make 1 sigma bond, and then the remaining p orbitals can form off-axis bonds, pi bonds. So I get 2 pi bonds and 1 sigma bond. That's a triple bond. So alkynes, of course, have this pattern, a pattern of sp hybridized carbons forming 1 sigma bond on axis and 2 pi bonds off axis. sp2 hybridization can also form a sigma bond on axis. Okay, so it has 3 lobes separated by 120 degrees in the plane, in the xy plane, or whatever you like to call it. That's kind of arbitrary, but one of the bonds overlapping with the second one in the plane, that is the on-axis one, is the sigma bond. And then the single p orbital, atomic p orbital that did not partake in the hybridization is also available for bonding, forming an off-axis bond. Therefore, I form 1 pi bond in addition to the sigma bond. That's a double bond. Okay, so the ethene molecule is a great example of this bonding pattern. So that's basically trying to explain the symmetries that I find in my chemistry toolbox. And the valence bond theory is a really good description of those symmetries, of those bonding symmetries. But what this theory doesn't do a really good job at is to explain why those bonds form in the first place. Why does a bond form? Okay, valence bond theory doesn't explain that very clearly. It basically tells me something about if it forms, here is the possible orientation in space of the electron distribution. Okay, using this new way of describing the orbitals. It doesn't explain why the bond forms. In terms of why does the bond form, I need something that says, well, it is more favorable to be bonded than not to be bonded. And that's an energy argument, right? I have to look at the energies to determine whether the new situation of bonding is more favorable than the 2 atoms not bonding. So I have to look at finding orbitals that are energetically more favorable than the orbitals that do not bind. Okay, so what I'm going to do is something very similar, in fact, but it has a very different base, a very different kind of motivation. I'm going to make linear combinations of atomic orbitals, LCAO, where I have 2 inputs, namely an orbital from atom number 1, or A, okay, so that is from atom A, and then an orbital from atom B. This is new, okay? Remember, in valence bond theory, what we did, we focused only on 1 atom, the central atom of the molecule, let's say, and then see how we can manipulate the atomic orbitals in such a way that the correct symmetries are coming out, right? So I'm only focusing on 1 atom here. But here, it's very different. It's a very, very fundamental difference. Here, I'm focusing on 2 atoms, right? I'm going to make a linear combination, not of the orbitals of 1 atom with themselves, but of 2 different atoms, okay? So A and B. I'm going to make a linear combination of 2 different systems, system A and system B. That's what I'm going to do. I'm going to assume that this new way of describing, of making this linear combination, provides a better description than the individual orbitals, okay? I'm going to make 2 combinations, an addition and a subtraction. What is the reasoning behind this? Well, the addition is the constructive interference between the 2. The subtraction is the negative interference, the destructive interference. So constructive for plus and destructive for the negative symbol. If I do this, it turns out that this actually has some really interesting properties. So making the linear combinations, the plus and the minus version of 2 independent systems, A and B, gives me 2 new orbitals that are, turns out, a much better description of the individual orbitals, of the individual atoms. One of the properties that it has is that this system can be normalized. Okay, so let's try to do that for the plus orbital, the one with the plus sign, which is the constructive interference one. If I multiply with itself and integrate over space, what I'm getting, just fill out. So just fill it out. I get basically the square of the orbital of A, square of the orbital of B. And then I got, of course, I get the combination of the 2, the cross term, okay? And that is basically, psi A times, say, psi B. Now, the good news is that psi A is a normalized wave function. Okay, that is true because the atomic wave functions are all normalized. So if you multiply it by itself, that's simply the normalization condition for this orbital. So this whole thing is 1. Same for psi B squared, also 1, normalization condition for psi B. But the last term here is not so easy to determine. Why not? Previously, we have said, well, if you have 2 wave functions from a complete set, then the overlap integral must be 0. So this last part must be 0. But that is not true. Okay, this is not 0. Okay, this is not equal to 0. Why not? Because A and B are 2 different wave functions from 2 different systems. They're not part of each other's complete set. Okay, they're 2 independent wave functions. So I have no guarantee that this thing is going to be 0. In fact, in most cases, it is not. So this is very different, folks, from what we've talked about before. If you have a complete set of one system, then this overlap integral is going to be 0. But if you take 2 elements from different sets, put them together, of course, that overlap integral does not have to be 0. It's physically a different situation. So what I can write is the following. I'm just going to say this overlap integral I'm going to call S. The first 2 integrals I can solve. Those are 1. So what I'm getting is 2 times 1 plus S, n squared, and I say that's going to be 1. So that basically means I can solve for n. So I can normalize this wave function, right? 1 over 2 times s plus 1, the square root of the whole thing, is going to be my normalization constant. Another thing I can do is I can check if this negative and positive combination actually forms an kind of an orthogonal set, a set of only 2. But I'd like these 2 wave functions to be orthogonal. That means that they are unique descriptors. They have no overlap with one another. If they don't have overlap, then they are both a unique descriptor. Okay, so one does not contain any information about the other one. So the plus and the negative version, the constructive interfering and the destructive interfering wave functions, if I multiply them together, integrate over space, I get the following integral here. Okay, so the first one is the plus combination. The second term is the negative combination, the minus combination. If I multiply this out, the good thing is that there's a plus sign here, negative sign here, so the cross term is going to be averaging out. Okay, so what I'm getting, I'm simply getting the normalization condition of the first one minus the normalization condition of the second one. And that means 1 minus 1 equals 0. Lo and behold, these 2 new wave functions that I'm making of 2 independent systems, A and B, are orthogonal. This is really good. Okay, so I have now 2 wave functions that are orthogonal to one another. That means they are unique descriptors. Okay, the psi plus and the psi minus, they're not related. They are completely orthogonal. That means they form basically a complete set in and of themselves. That is a good property to have for describing my new scenario here. So let's have a look at that in the last slide right here. The plus wave function here, if I take the modulus square, which is basically the probability distribution of where the electrons can be in this new descriptor, I find this expression right here. Now we can analyze what it means, because the first part is simply the distribution of the electron when it sits on atom A. That's the distribution of the electron when it sits on atom B. Nothing new here, but that is the new information. This is the constructive interference of the 2 separate wave functions. Okay, and that is what we call the bonding between 2 atoms, an enhanced electron density because of this positive combination. Because of constructive interference, you get an enhanced component, a region in space where it's more likely for the electrons to be together. The negative combination is the same story, atom A and atom B, but now a negative symbol here, meaning that it's destructive interference. It's going to be less probability of finding the electrons in this region when they combine in this fashion. Okay, so what I'm getting here is the plus combination, the negative combination. This is what they look like in terms of their amplitude, the amplitude of the wave functions. Okay, so combination of both. Okay, so two s orbitals, let's say, it peaks, goes down, and then in the middle they combine favorably, or they subtract, in which case they do not combine favorably, and I get a node. All right, so the bonding and the antibonding probabilities, which is the modulus square of each, you can see it beautifully here, that here you get an enhanced likelihood of finding the electrons right there, and here you get a null or a node, which means no likelihood of finding the electrons here. That's why this is called antibonding, and this is called the bonding. So we'll talk about this on Monday, but the bottom line is that these new wave functions that I'm describing here are much better descriptors of what's happening when you put two atoms close. These two wave functions that are orthogonal are unique descriptors that kind of give me information of what is happening when you put two quantum systems together. In one way, they can amplify one another, and in another way, they can mutually destructively interfere one another. Okay, so these are the two likely scenarios that must happen, and this will tell us on Monday why bonding forms, and in some cases it doesn't. All right, I went over time, so I'm going to stop right there. Sorry for going 3 minutes over time, folks. Hopefully this was entertaining enough. Any questions?
Could I ask a question?
Of course.
So when there's a node, that would mean that there's no way for the molecules to bond to each other. Is that what that would mean?
Yes, so we'll zoom into this on Monday in more detail. Okay, so some of this may look familiar to some of you when you had freshman chemistry. We talked about similar things, but we're going to look at it much more carefully this time in terms of actual wave functions and why you have an enhancement and a depletion in these two cases. So indeed, the negative or the null here means that if you're going to put two electrons close to one another, two atoms close to one another, that there is a combination, there is a state that forms that says, no way, Jose, there's going to be no electron density in between these two atoms. And if there's no electron density in between, that means that the nucleus here and the nucleus here, which are positively charged, of course, with some number, that they will be very much repelling one another. There's no offset here of negative charge. Usually when you put negative charge here, you can offset the repulsion of these two nuclei. So this is going to be antibonding because this is literally driving the atoms apart. While here, the plus charge of the nucleus, I'm doing 1 plus, but of course it could be any number, right? So n, right? So this is the two similarly charged nuclei. They can repel one another. But if I have electron density here, it can offset that repulsion and therefore keep the system together. That is the reasoning behind this.
Okay, that makes sense. Thank you.
Mm-hmm.